Okay, our next speaker is Marie Cockx. Is she here? Thank you, Marie. And she's actually replacing Sebastian Ullmann, but giving the same talk, which is on measuring codend dynamics and its impact on catch welfare.
Thank you.
There you go.
Thank you. No problem. Thank you. Hello, everyone. So as you can see, I'm not Sebastian. Sorry. So my name is Marie Cockx, and I'm a former student of Sebastian's. I actually did my master thesis on this subject, and it was a collaboration between ILVO in Belgium and DTU Aqua in Denmark. So this work has big objective to see what is actually happening inside the gear, and in this case the codend, to better understand what are the mechanical forces that are acting there and how does that affect injury. So we are still talking about flatfish. Yeah, okay. So fish welfare in fisheries has not received a lot of attention until recently, and that is a problem for several reasons. First of all, so the fish are really getting injured in those nets, as Peek has showed us. And we can see all different kinds of injuries. They're also getting stressed, and they suffer from a lot of things, such as hypoxia, etc. And that is a problem for several reasons. First of all, of course, we want to avoid unnecessary suffering for the fish. Then often those fish with a lot of injuries, they are showing less product quality, so this is a big problem. It can also be a problem in terms of selling price and so on. And they also increase the amount of catch that gets wasted, because if a fish dies before landing, or if it could have been released and it cannot because it died, it's also a problem. So they increase the amount of catch that is wasted. On the other hand, at the same time, I'm not sure where I have to point this. Okay. So on the other hand, we are seeing more interest in this topic from customers. First, because they are not only looking at fish that is sustainably harvested in terms of stocks or habitat, but they can also have. They also want maybe to buy fish that is ethically captured. And also, we are seeing a more organized interest in this topic, and this platform is a great example of that. A big problem when we are doing welfare research, catch welfare research, is that we struggle to have a real idea of what is happening to the fish. What we are assessing is the injuries at the end, or the amount of time they spent in the net. But we really struggle to have a really precise idea of what is happening for them. So other industries have actually come up with a solution to that, is the use of, as you may see, some sort of crash test dummy fish. So those are sensor-like fish, as you can see some example there, that are getting data on what is actually happening to the fish. It could be how many times they are hit, how much time precisely each fish stays in the net, and so on. So yeah, what we are looking for is a real dose response of what is happening, to really have an idea of what is happening to the fish. Okay, so this study is also focusing on beam trawling. So as Peek explained already, it's a widely used method in the North Sea to catch flatfish, but also shrimps. And the codend is where, so it's the very back part of the net where the fish is actually accumulating. And Peek had a really nice video of how what's happening there. And here it's represented with balloons. So as you may see, the codend is actually not static during the fishing. It moves back and forth due to the motion of the waves, of currents, of the movement of the vessel, etc. And this is where things get rough for the fish. So they get crowded, they are crushed against each other. If we have, for example, big stones in the net, they also are there and crushing the fish. It's really like a washing machine for them, and it's really not good for them if they want to be injuryless. So the objectives of this study, first we wanted to really quantify what is happening inside the net. So for that we used, as you may see, the first picture is an accelerometer, and we used two of them. One we placed in the codend, so at the back of the net, and another one we placed at the aft of the back deck of the ship, to have an idea of how the movement of the ship and how the movement of the codend, how they relate to each other, are they linked to each other? They should be, because they are linked. And then we also want to connect that with actually the sea state, because it is known that it is the sea state that is causing the vessel and ultimately the gear to move. So for that we use data from nearby floating buoys at sea. And then the second thing that we looked at was fish condition. So we measured some kinds of injuries to the fish, so scale loss, point bleeding, bruising, and also damage to the fins. And we also wanted to look at other factors to see if those factors induce injuries to the fish. So fish length, towing duration, catch weight, and also the proportion of injury-inducing species, for example, crabs or fish that had big spines, so that could injure each other. So this study we did, so we collected data during the demersal young fish survey in Belgian coastal waters in September 2024. So over the course of 4 different days, consecutive different days, we visited 11 sampling stations, and for each of those stations we performed 15-minute tows. In total, we collected 90 dabs, 28 places, 19 flounder and 11 sole. And as I already explained, we used those 2 accelerometers. They were both inside aluminum cases to avoid for waterproofness. And then for the codend one, we put it into a small mesh bag that was itself attached inside the codend, approximately 1 meter from the very back of the net. And the other one, the other accelerometer, same aluminum case placed on a cage that was fixed at the back of the deck. So then what we did with those accelerometer data, so the whole compiled 3 axis acceleration, and we put that in together as an acceleration magnitude signal, as you can see on the first graph. So on the x-axis is the time, and the y-axis is the acceleration. But then what we were interested in was the frequency of those accelerations. So at which frequency a certain repetitive movement is happening. And for that we use the fast Fourier transform, so FFT, and that shows us, for here you can see on the second graph a big peak that shows at this certain frequency that many acceleration is happening. And what we did then is we took the maximum amplitude of each stations for both the codend and the ship, and we took those data for response. Then, for the injury scoring, first we used scored based on an ordinal scale, so based on the surface of the fish that was affected by the injury. So, for example, if we have a sole that is 50% of the scales are gone, then it's a 2, and so on for every types of injuries. Unfortunately, we did not use those scores for the data analysis because they are really hard to work with statistically, and our sample size were really small. So we switched to presence-absence, so a binary response, so presence of scale loss, presence of point bleeding, and so on. But we still kept a continuous response for the bleeding injuries, so we combined together point bleeding and bruising as a single bleeding score. That was the mean of the point bleeding and bruising score, and we did that for the head, the body, and the tail fins region of the fish. So for the statistical part, so we did first a univariable analysis, so each response, how they relate to the presence of injuries, For that, we used the general and linear mixed models. And then for the continuous response, so the bleeding score was with linear mixed models. And then we also did multivariable analysis with for our model building. So that was to see how those responses, they are linked with each other. And for that, we used wave height in the null model to see, because we were hypothesizing that the C state was the driver of injury. And then also, we did the same thing, but with the acceleration maximum amplitude, but not for the codend, for the ship. And this is where things get a little bit complicated for us, because what we wanted to do, we couldn't do. Why? As you may see here, on the left-hand side, we have the results from the FFT, so actually the same that I showed before for the ship, and all stations were quite looking like this. But on the right-hand side, you have the results of the FFT for the codend, and as you may see, they are much more chaotic, let's say. They don't show clear peak, unless what we see for the ship. And that is a problem, because we could not really extract data that would represent the movement in the gear, unfortunately. So what we also did to confirm this, that something wrong happened, is we did some correlation, and we found correlation between movement on the ship and wave height, so this makes sense. There are waves, the ship is moving according to those waves. But for the codend, we could not find any link between either the movement of the ship, but they should be because they are linked with each other, and same for the waves. So we decided to keep the movement of the ship as a proxy for the movement of the gear, which is not ideal, but yeah, we couldn't do something else. So now we're going to look at every injury. So the stars, they represent a link, whether positive or negative, between one of the factors. So here we have wave height for European flounder. And so this means that there is a link between the presence of scale loss and wave height for European flounder. Then for the model building, so this is a multivariable analysis, we also see that for your flounder, we have a relationship with wave height, but this time also for common dab. So here you have a graph that represents the proportion of common dabs with presence of scale loss, depending on wave height. So our sample size were really small, so I will be quick on this, but yeah, we can see some kind of relationship, but unfortunately it was not really strongly supported by statistics. And same for flounder. There is a link, but it's not really, we cannot be strongly sure about that. Then for fin damage, same flounder, we saw a bit of a relationship with ship acceleration and gear deployment. And for sole, ship acceleration and catch composition, so the amount of injury-inducing species that we have in the catch. Same for the multivariable analysis with wave height, for European flounder and also fish length. Same. So now we are moving on to the bleeding scores. So we have both presence, absence of bleeding, but also the amount of bleeding that we saw. So here for common dabs, we can see some relationships with movements in the form of wave height. With the second one is wave period. Same for dabs, but also with weight, etc. You can see here the different relationships that we found. However, for the multivariable analysis, we had much less relationship. Then body bleeding, you can see that it's consistent between the univariable analysis and the multivariable analysis. Here only place we saw a relationship between ship acceleration and length, but with body bleeding. And finally, for tail and fins injury, we could not find any relationship for any species. And I think that it's because, so I will say it now. So we had really short tows, so only 15 minutes, and that is really not what is happening in commercial conditions. So unfortunately, but fortunately for the fish, but unfortunately for the study, the fish were in excellent condition. If you remember the pictures that Pig showed with the A, B, C, D state, most of my fish were with A. So I really struggled to find injuries, which is fine. but it would have been nice to have some fish injured. So yeah, in the most common injury that we found was actually tail and fins bleeding, because there was a lot of bruisings in the tails. So there was not really a lot of variability. And I was really trying to find injuries. So whether I found a small spot on the tail, I would, yes, it's there. So a 1, which is not really a good thing to do, but yeah, was a bit desperate. So in the end, as I said before, what we wanted to do, so measure codend, sorry, I'm talking a lot. Showing codend movement was not possible because of the struggle we had with the accelerometer. And we think that is because, so as I said before, the accelerometer was in a mesh bag, but it was allowed to move within this bag. So we think that what we measured was actually the accelerometer moving around in the mesh bag, and it was not possible to have a clear pattern of what was happening to the whole codend. So a solution would have been to secure the sensor to the codend, but we are also curious. Maybe some of you have ideas on how we could do that, maybe with cameras, if light permits, or would have been perfect to have a dummy fish, as I showed before, to actually record a lot of data, and we know exactly what is happening, but maybe this exists, and some of you have a solution for me. And yes, of course, we still show that the vessel was highly correlated with wave height, but we were expecting that. And finally, we could see, even though it was not really statistically strong, we could still see that some injuries were linked with at least ship movement and wave height. So that is a good thing, but as I already said, the catch was in really good condition. There was no overall pattern. We could not say, yeah, for this amount of movement, we see this injury a lot. So this study was still really preliminary, I would say. But yeah, we would be. It would be really nice to be able to do it on a bigger vessel. Really, the ideal would be to have actual commercial condition. And I will also have a last word about something that we call Belgian compromise, because actually this study was supposed to take place on a much bigger vessel for a longer time, but because of a lawsuit between Belgium and the company being responsible for our research vessel, we had to really scale down the study a lot. And actually the net that we used was the shrimp net, and all of the fish that I got they were below minimum retention site. So this is really a preliminary study, as I said, but if it gives you idea on how we could do it better, please feel free to contact. Thank you and have a nice lunch.
We have time for one question. Luca, because you were ignored earlier.
Thanks a lot for the presentation, very good. I just wanted to ask you one thing. Do you think that maybe the fact that you actually didn't fix the accelerometer into the net, let's say, is actually a good proxy what the fish is actually experiencing? Because the fish will be, let's say, moving all around. Yeah. And also, you were trying to point out, for example, a specific frequency. But you noticed that, for example, this accelerometer, like in the codend, was not having a clear pattern. Yeah. What can be itself, for example, the frequency, the variability in the frequency, yeah. For example, a proxy of what the fish can really experience. So okay. The fact that it's in the washing machine, yeah. For example. So maybe you could use the variability okay. Into the frequency as a proxy okay. for damage and injuries.
Perfect, yeah. Thank you very much. Yeah, that's a really good idea. And yeah, of course the fish are moving, but as this was really a first step in those kind of study. We wanted first to have an idea on the codend itself, and then maybe in the future we can move on and see the variability that you mentioned. But first, would be nice to know what is happening for the gear, if it really moves a lot or not that much, and it's just the fish that move by themselves, I don't know, maybe. So yeah, thank you for your suggestion.
Thank you.
Thank you very much, Marie. That was excellent.